Well, thank you very much for inviting me to join this webinar. Great pleasure. I've been asked to talk about energy consumption of EVs and charging equipment. So that's what I'm going to talk about. I think it's worth spending a bit of time thinking about how we can charge heavy vehicles. And in particular on the motorway network, I think that the problem of charging vehicles in cities, urban operations is pretty well solved. And most urban vehicles are becoming electric quickly. But for long distance charging, there are different ways that we can do that. One is that we can charge trucks at truck stops, and that looks something, or will look something like this picture on the left. Another is that we can charge trucks at warehouses. And this is going to become increasingly important for reasons that I'll explain later, but particularly if we want logistics to roll quickly without time delays due to charging, it's pretty well essential to be able to charge vehicles while they are in their warehouses. There's battery swapping, that may be an option. I'm not really going to talk about battery swapping other than to say that it is significantly more expensive, it seems, than static charging, and it's not really favored by European OEMs for a bunch of reasons, which I would be happy to talk about if anybody else wants to ask questions about that. I don't think battery swapping is going to be a thing in Europe. There's also dynamic charging, and some of you will have seen the demonstrations of the Siemens e-highway system, which uses overhead contact lines to power trucks. There's another system in Sweden called Elon Road, where vehicles pick up their power from conducting rail in the road, and that looks interesting and hopeful. These have big advantages in that vehicles don't need to stop to charge, and they can have much smaller batteries, so they can carry a full payload. So there's a lot to be said for that kind of dynamic charging. But nothing much has really changed. You know, these are trucks in 1907, electric trucks in 1907 charging. They were charging in their depot, and we still have the same sort of problems. We just have better batteries and better tires than these vehicles. Some better materials as well, but the same problems exist. So I just want to talk a bit about some of the efficiency issues that specifically we've been asked to talk about. And I want to start off at a high level, looking at electricity coming from a renewable source of electricity. So if we say have renewable electricity here, 100 kilowatt hours coming from solar panels or onshore or offshore wind, maybe nuclear power station if that's your, or hydroelectric, gets transmitted via the electricity grid. And as Tas has said, there are losses. Those losses on average in the UK are about 10%. So you get about 90 kilowatt hours by the time it gets to the destination. Then there is a process of converting that AC electricity to DC and charging a battery, and then taking that electricity and putting it into a battery electric vehicle. And each of those processes are inefficient. And by the time we get to the battery electric vehicle, we've got about 69 kilowatt hours left of the 100 that we started with. And I think it's important to realize that this is any kind of electric vehicle. It might be a truck or a car. It might be a scooter or a bicycle. It might be an electric ship or a ferry. It could even be an electric aircraft in future. So they all suffer this same set of losses. If alternatively you take your 100 kilowatt hours of electricity and you make it into hydrogen, nice green hydrogen, which you make by electrolysis, you convert your 100 kilowatt of AC electricity to DC, and then you electrolyze water. That's about 75% efficient. So you end up with about 71 kilowatt hours of green hydrogen. And you take your hydrogen, you compress it, and you put it in a tank and transport it. And then you decompress it and put it into a fuel cell. And the fuel cell turns it back to electricity again. So it goes back from green to yellow, back from hydrogen to electricity. And the fuel cell is only 50% efficient. And that is the nature of fuel cells because they have to satisfy the laws of thermodynamics. So by the time you get out of the fuel cell, you've got 26 kilowatt hours of electricity left. You put that into your electric vehicle, and it's got about 23 kilowatt hours. So you've lost 3/4 of the energy that you started with by converting electricity to hydrogen and back to electricity. Unfortunately, you have to pay for the electricity that's generated, not the electricity that you use. Somebody has to pay for those losses. So green hydrogen is a very expensive way to fuel your vehicle because it takes so much more electricity to power the vehicle. The third system that I showed you there is the dynamic charging system. Dynamic charging, or ERS, electric road system, has the advantage that you don't have to go in and out of the battery. For much of the electricity doesn't have to go in and out of the battery. That saves quite a lot of losses. It means that by the time you power the vehicle, you've got about 77 kilowatt hours at the wheels of the vehicle. And that is the most efficient way that you can run an electric vehicle. Now, it's important to realize that these efficiency numbers have real meaning. They're very important because if you want to generate, for example, if you want to power all the trucking in the country, we know how much how much energy roughly it takes to power all the trucking in the country. What you have to do is to generate enough renewable electricity to do that. And let me show you how this comes out. If you use the ERS, that's the most efficient system to power the UK's trucking, you need about 11 gigawatts on average of additional power. And that, if you did it with onshore wind, that would be a circle of 5,300 square kilometres, which is shown to scale on the map there, with 3,500 onshore wind turbines. That's the most efficient way to do it. If you did it by green hydrogen, which is the least efficient, because of all those losses, you have to generate a lot more electricity than actually gets to the vehicles. And so you need a lot bigger land area of wind turbines if you're going to generate electricity, create hydrogen, transport the hydrogen, convert it back to electricity in the fuel cell, and then use that to power the vehicle. And in fact, you need 3.3 times more than the ERS. So that means that you need 3.3 times more land area, 3.3 times more turbines, 3.3 times more grid connections, 3.3 times more repair people and spare parts and helicopters, and it's going to cost 3.3 times more. So we can be pretty well definite in our knowledge that it will cost 3.3 times more to power a hydrogen-powered vehicle than to power an electric vehicle. And for that reason, it's very unlikely to happen because the operating costs are about 3 times the cost of running an electric vehicle. In fact, the capital cost of the hydrogen vehicle is about double the capital cost of an electric vehicle, and we don't see that ever changing. So by the time you have an electric vehicle, which is pretty much on parity with diesel for much of its operations nowadays, but a hydrogen vehicle which costs 2 times more to buy and 3 times more to run than the electric vehicle, we can see that it's a really very expensive proposition and extremely unlikely that it will ever be a thing. So I think we can pretty categorically count out hydrogen-powered vehicles for freight and logistics, just as they've been wiped out of the car market. Now, I was asked to talk about efficiencies of charging vehicles, and so I'm going to do just a little bit of a deep dive into this. And my picture starts at the power meter, the meter that comes into your depot or your warehouse. That's um, the grid connection of your warehouse. And I'm ignoring what goes on upstream of that. Uh, it's very important, but I'm not considering it in this slide. Now, you take power and you put it into a charger, and what that does is it makes it into DC power, and you put that charger into the battery of a vehicle. From the battery, it goes into an inverter, and from the inverter, it goes into the motor and drivetrain of the vehicle, and that gives propulsive energy, which overcomes the weight, the inertia, the rolling resistance, and the aerodynamic drag of the vehicle. And the efficiencies of these things are all shown except for the efficiency of the battery. But it's important to realize that we're going from AC power in the electricity grid to DC power going into the battery, DC power coming into the inverter converts it back to AC, and the motor is an AC induction motor driving the vehicle. Now, what goes on in the battery? Well, the battery has really three main things that happen. First of all, there's some internal resistance charging the battery. And that means that not all the electricity that goes into the terminals of the battery actually appears in the state of charge meter, in the charge meter that you've got in the truck. That's there. So there's the state of charge meter measures the cell energy. So we've got electricity coming in, goes through the internal resistance, and there's some losses. We've got a meter, the state of charge meter, which measures the cell energy, and then when the electricity comes out of the cell, it goes through another internal resistance, and it comes out and goes into the inverter. And each of those have not imperfect efficiencies, something like 96%. So if you have 100 kilowatt hours state of charge in your battery, then you will have had 104 kilowatt hours coming into the battery. And because of the losses in the charger, you'll have about 112 kilowatt hours coming from your meter. So 112 kilowatt hours, you're going to lose about 12 of them, something like that. And you've got about 100 that's going to appear in the state of charge meter of your vehicle. Now, exactly what the losses are particularly depends on how fast you charge. The faster you charge, the higher the losses through the internal resistance and through the charger. So it may not be 112, depending on how fast you charge. It could be 115 or more. So, but you're going to lose a significant amount of electricity going from the power meter into the battery. Now, of course, you have losses around the other part as well, so that by the time the energy goes into propelling the vehicle, you've got about 84 kilowatt hours actually propelling the vehicle forward from the 100 that you had in the battery. So to summarize that, to put 100 kilowatt hours into your battery and measure it on your state of charge meter, you have to purchase 112 kilowatt hours or something from the grid through your meter, and it depends on the charging rate and exactly what it is. So don't expect them to be equal. Don't expect to see the same amount of energy in your battery as you bought from the electricity, from the charging provider.
Sorry, David, just one thing. My apologies. We are very running late with this
Okay,
presentation as well.
just
So,
be a second.
yeah,
Yep.
in 1 or 2 minutes. But thank you.
Okay. So 100 kilowatt hours in the state of charge gives you about 84 kilowatt hours of useful work. And the important thing is you need to account for these processes in your energy calculations, in your ISO calculations, your GLEC calculations, because if you don't, you will get the wrong answer. So, for example, if you drive a kilometer or you drive 50 kilometers on your 100 kilowatt hours, have you used 100 kilowatt hours or have you used 112 kilowatt hours of electricity to drive whatever distance you traveled? Clearly, the vehicles used 100 kilowatt hours, but the total amount delivered from the electricity connection was 112. . 112. There are some penalties when you do logistics with electric vehicles. A 44-ton vehicle carries 29 tons. A 42-ton vehicle carries 22 tons. And payload loss is about 24%, 7 out of 29 tons. That means it takes 4 battery electric vehicles to move the same freight as 3 diesel vehicles. That means you've got about 33% extra cost, or about 33% more energy actually consumed at the wheels. There is a time penalty, and that time penalty comes from charging time. You have to charge a vehicle every 4 hours after it travels about 320 kilometres. It takes about an hour to charge it, so you're charging about 20% of the time. 20% of all trucks on the road have to be charging. In the UK, most rest stops occur during logistics stops when the vehicle's loading and unloading. What that means is that you have to charge during driver breaks at logistics facilities, which requires a large grid connection, or you have to take an extra stop at a public charge point, which will cost you 20% extra cost. So this is very important. There's a payload penalty for heavy loads. There's a time penalty, which you can only fix up by having a big grid connection in your warehouse so you can charge during the time the vehicle would stop anyway. How
So,
many
Da-
is
David, my apologies. I really have to stop you here so we can have some time for the rest of the
yeah,
presentations. And then you can also take it up again during the panel session or even after the webinar. We can
well,
direct
let me
questions.
point out the last point on the conclusions there. Those logistics penalties must be overcome if we're going to roll out EVs. Unless you can overcome the weight penalty and the time penalty and the grid connection problem, we will not be able to roll out EVs. And so everything we're talking about will be a waste of time.